Greetings and welcome to this lecture. We are in module 7, lecture number 3, weak inversion. In this lecture, we will discuss some special conditions in weak inversion, body reference model and source reference model. These are the learning outcomes of this lecture, which will help you to understand that how the current flows in weak inversion. First of all, this will help you to understand how we define that our MOSFET is operating in weak inversion or strong inversion or moderate inversion. So, let us start this lecture with a quick recap. In previous lectures, we said that we will define the current in terms of the terminal voltage as W divided by L mu into COX dash into VGS minus VT into VDS minus alpha times of VDS square divided by 2. This was defined in strong inversion region of operation, and this current is nothing but IDSN, which is non-saturation current. We also said that the current beyond a pinch off voltage, it gets saturated, and it was defined as IDS dash, which was given by W divided by L mu into COX dash VGS minus VT whole square divided by 2 into alpha, right? And we saw how the current varies with VDS. So, this is IDS, and if you plot this current, ultimately at certain point when the slope of this curve becomes 0, you can get this VDS dash, where VDS dash is the boundary which decides between the non-saturation and the saturation region of operation. So, VDS dash is defined as VGS minus VT divided by alpha. Beyond this value, it got saturated. So, the current is saturated with this IDS dash value. So, in previous lecture, we have also seen that we can simplify this analysis in terms of eta, where eta was defined as 1 minus VDS divided by VDS dash, where VDS dash is given by this, and we can simply write a single equation of current as IDS is equals to IDS dash into 1 minus eta square, right. Then we argued on the dominance of alpha. We said that in general hand calculation, we considered that alpha is equals to 1, but that gives erroneous result, meaning the alpha is somewhat underestimating or overestimating the bulk charge. We said that if we plot minus QB dash by COX, then this graph was look like this between surface potential psi S0 and psi SL, and we need to properly capture this this QB dash behavior. There are few possibilities. One is the line A, where we are considering source as a reference. The another is line C, where we considered the alpha is equals to 1, and there is another a line B which is actually predicting correctly. Thus, we argued that the value of alpha should lie between 1 to alpha 1, where alpha 1 is equals to 1 plus gamma divided by 2 times of root of psi S0, considering source as a reference. We also said that the value of alpha and gamma, it means alpha is equals to 1 plus gamma divided by 2 times of square root of psi SE, where psi SE is an expansion point, where psi SE is equals to psi SM for body reference model and psi SE is equals to psi S0 for source reference model. So, we said that the value of gamma and alpha is very important to tune to get a better fit of our model with the experimental data. Now, let us see what is the quality in weak inversion. We also know, we have already discussed about weak inversion, that the gate voltage is not that enough such that the inversion happens here, right. It is just the surface potential just reaches the value of 2 pi f, meaning if we plot the surface potential with respect to VGB, that is what we have done in our 2 terminal MOS structure, the surface potential look like this, and this point is defined as the weak inversion. below weak inversion, this point phi f there was a depletion, and above phi f and below 2 phi f there was a weak inversion. In the weak inversion, the surface potential is almost fixed to a value psi SA, which is a function of VGB, where psi SA can be given by this. Meaning, if we consider my transistor operate in the weak inversion, then none of the channel side will operate in strong or moderate inversion. In the sense, if source side is at weak inversion, then drain side may be at weak inversion or in depletion. Then I can say my transistor operates in weak inversion. This is the same argument which we have already considered in time of in previous lectures when we were discussing about strong inversion model, right. So, we are considering that VDB is equals to VSB, and this is not, and the gate voltage is not enough to cause inversion, and hence the surface potential here is psi S naught and the surface potential here is psi S L. Let us consider both the surface potential is approximately equals to psi S A, meaning both the channels are weakly inverted. If you see carefully, between source and drain, which the region which we called as channel, the potential is almost same. The potential is not varying between 0 to L, and hence the drift component of the current is negligible. We also said that IDS is equals to IDS1 plus IDS2, where IDS1 is a drift component and IDS2 is diffusion component. As we have said that in weak inversion there is no electric field along the X, right, then the diffusion dominates and not the drift. So, overall current equation can be represented in terms of IDS2. The two physical consequences in weak inversion, as we have pointed out, that QB dash is considered to be same and it is not varying with X, because QB dash is can be given by minus gamma COX into root psi S, right. If we talk about psi S at the source side, you can replace by psi S naught. If you talk about psi S at drain side, you can replace by psi SL. But as we are considering for the weak inversion, here both psi S and psi SL0 are psi SA. So, ultimately QB will not vary along the channel. The second point is no horizontal electric field is exist because it is in equipotential surface, and hence the drift component is negligible, correct. So, we need to only consider the diffusion component. Now, how can we go for a diffusion component? You remember from our basic theory of diffusion, if there is a semiconductor bar and there is a gradient in the concentration, let us consider the electron gradient N1 and N2, then the current through this semiconductor bar is can be given by approximately W into D into dN by dx. You should take care about the sign of this gradient of electrons, right. So, this is the current flowing in the semiconductor bar, let us ID, right, and this is the width of the semiconductor bar, that is W. Here D is a diffusion constant by using Einstein relation, which can replace as mu into phi t into dN by dx. The same approach we have already followed to calculate IDS2, which is nothing but IDS2. So, in general, as in weak inversion of operation, the current is dominated by the diffusion only. So, we are simply replacing IDS as IDS and rewriting this equation as W divided by L mu into phi t Qi L dash minus Qi 0 dash, where Qi L dash is the inversion charge present near the drain and Qi dash is the inversion charge present near the source. You can see from here also that these charges linearly varies along the channel between 0 to L, correct. So, let us simplify this model using our two known reference model. One is body reference model and one is source reference model. We have also derived few equations a way back when we were discussing about body reference and weak inversion and source reference models. So in body reference model, the Qi0 can be defined by this equation, which is nothing but minus square root of 2 into Q into Na into epsilon s, where these quantities are known to you, divided by 2 times of psi Sa, which is a function of Vgb only. Psi Sa is what? Is the surface potential in the weak inversion, into phi t e to the power of psi Sa minus V minus 2 phi f by phi t into e to the power of minus Vcb divided by phi t. You remember that we have considered a special case when we were deriving these equations in weak inversion. That is, when we plotted the surface potential with respect to Vgb, we got this kind of characteristic, and we said that this is the upper limit of weak inversion. At that moment, we wrote this equation, instead of psi Sa minus 2 phi f minus Vcb, we have written Vgb minus of Vm divided by phi t, and yes, the another term will come as e to the power of minus Vcb divided by phi t. This is phi t e to the power, correct? So this equation was derived for a special case, or at the boundary when this curves just bend towards the fixed value of 2 phi f, correct? Similarly, we can define the inversion charge at the drain side, which is QIL. Only difference is here in the exponential term, you will see that it is e to the power of minus Vdb divided by phi t. We will put back these two equations here and to calculate IDS, which is nothing but IDS is equals to W divided by L, some function which is only a function of Vgb, into e to the power of minus Vsb by phi t minus e to the power of minus Vdb by phi t, because this term minus this term you are doing right here, Qi L dash minus Qi0 dash, where this function, if you see, it is only a function of Vgb, which we are going to later replace by this. So this is a body reference model which will give you an idea how my current changes with respect to Vgb. In addition, how the current is changing with respect to Vdb and Vsb. Now, if I want to show the current change with respect to Vsb, this is a good model to show, because I do have some explicit function of Vsb in my current equation. In the other way, I can reframe the equation in terms of source reference model, which was given as IDS is equals to W into mu into phi t divided by L Qi0 dash minus Qi L dash with a negative sign out, right? What I will do is minus W divided by L mu into phi t, take Qi0 dash common, 1 minus Qi L dash divided by Qi0 dash. If you take these values from the previous slide, you will get that Qi L dash divided by Qi0 dash, every parameter will get cancelled, only you will left with e to the power of minus Vdb minus of minus e to the power of minus Vsb. So ultimately you will left with e to the power of minus Vdb minus Vsb divided by phi t, and this can be written as e to the power of minus Vds by phi t. So this term can be replaced as e to the power of minus Vds by phi t. We will put back this equation in here. We will get IDS is equals to W by L into mu into phi t. Now minus of Q naught dash, again you can take it from here, right, which is minus and minus sign, this minus sign and that minus sign will be plus. So you can rewrite as square root of 2 into Q into Na into epsilon s divided by 2 times of psi Sa, which is a function of Vgb. There is another phi t term is here, e to the power psi Sa Vgb minus 2 phi f divided by phi t. This is the function of Vgb. So that is what we have taken from here, into 1 minus e to the power of minus Vds divided by phi t. So this phi t and this phi t, it becomes phi t square. That is what here it is coming up. In Im it will come, yeah, right. So W divided by L mu into phi t square into square root of 2 into q into Na into epsilon s divided by 2 times of psi sa Vgb. As I have already explained, considering the special case, we can simply replace this psi sa, which is a function of Vgb minus 2 phi f, as Vgs minus Vm by n times of phi t, where we plotted this graph as respect to Vgb and we got this type of point. This point was defined as Vmb and you are plotting surface potential. However, if I will replace this axis in terms of Vgs, then this will become what? Vm. We have already discussed what is Vm and what is Vmb. Vmb is nothing but V flat band voltage plus phi naught plus Vsb plus gamma times 2 or phi naught plus Vsb. So if I want to represent in terms of source as a reference, I need to represent as Vm. So Vm is nothing but Vmb minus of Vsb, which is nothing but V flat band voltage plus phi naught plus gamma into phi naught plus Vsb, right. Here it is not T, it is phi f. This is a typo. So here the Vm is equals to V flat band voltage plus 2 phi f plus gamma into 2 phi f plus Vsb, where we have taken phi naught as 2 phi f, correct. So the overall equation of the drain current is can be represented as this, where this Im dash is nothing but mu into square root of 2 into q into Na divided by 2 times of 2 phi f plus Vsb dash into phi t. What is Vsb dash? It is a specific value of Vsb, because we are considering this case for a special value of Vmb. Only at that value this relation holds good. That is what, if you want to show the variance of Vsb on the drain current, then this is not a good model. The good model is body reference, because in the body reference there is a Vsb term directly coming into picture. However, for the other sense, the source reference model is good enough, which shows that how my drain current varies with Vgs. So instead of Vsb, if you are interested in how my drain current shows or variation with respect to gate to source voltage, this is a good model to go with. Now let's plot this curve in respect to Vds. So we have seen that IDS in weak inversion is approximately equals to some constant, let's say C, into e to the power of Vgs minus Vt divided by n times of phi t into 1 minus e to the power of minus Vds divided by phi t. So this is a general expression where the current is exponential dependent on Vds as well as the exponential dependent on Vgs. We will see both of the perspectives. Let us consider the first perspective as we are varying Vds. Now if you increase Vds a bit, what will happen? This term will be negligible because it is negative exponent, and if it is negative exponent, this term will gone. Just even a small increase in Vds, let us say about 3 times of phi t, correct, where phi t is what? 26 milli electron volts or millivolts if you are representing in voltage, and if you are representing in energy, it is 26 milli electron volts. So phi t is 26 millivolts, just about 3 phi t, what will happen? This can be neglected, and the current is completely dependent on only Vgs. So for a particular Vgs value, let us say this is Vgs1, Vgs2, Vgs3, right, you are just increasing a drain voltage a bit and the current becomes constant. It is not dependent on Vds because this term is gone. Here the another thing is, as we have seen, if you increase Vds, let us consider you are increasing Vgs now. For Vgs equals to 1, this graph is there. For Vgs is equals to 2, the current is now exponential dependent on Vgs by n times of phi t. So this difference is now exponential, not quadratic as we have seen in strong inversion condition. So the behavior of drain current versus drain voltage in weak inversion is can be given by this. Here this is a moderate inversion boundary, right. The more interesting case in weak inversion will be come up when you draw the current IDS with respect to VGS, because it is clear that the current is exponentially dependent on VGS. So let us plot that graph also in log scale. So again I am rewriting that equation as I is equals to some constant into e to the power of VGS minus VT divided by n times of phi t into 1 minus e to the power of minus VDS divided by phi t. For the sake of simplicity, again I am capturing this term in C, because I need to calculate what is the relation of IDS versus VGS. So IDS, which is equals to, let us say, C1 e to the power of VGS minus VT divided by n times of phi t. The better way to represent is take a log. Log of IDS is equals to log of C dash plus VGS minus VT divided by n times of phi t, right. Now we will define another term here which is called sub-threshold slope. What that means is, so suppose if we are going to plot a log ID versus VGS, then the curve look like this, because it is exponential dependent. Taking log in the y axis, it is almost linear, right. So this is the weak inversion zone. The weak inversion zone is sometimes also called as sub-threshold region, right. In this region we are getting a linear curve, almost a linear curve. Now we will define this slope as a sub-threshold slope. Sub-threshold slope. Sub-threshold slope means what is the minimum gate voltage required to change the current by a decade. Let me explain you like this. Suppose you are increasing the gate voltage and your current is increases like this, and this point you marked as on condition, right. Now this point is marked as off condition. Now what is the voltage you need to apply such that you can go from on state to off state? How much voltage you should require, how much voltage you should apply here such that you can go from on state to off state. So that slope decides the turning off condition of your MOSFET, and it is a very important parameter as far as MOSFET is concerned. So how we define is, let us consider this point of current is 10 to the power of minus 7 and this point of is 10 to the power of minus 6. So to reduce the voltage from this point to this point, the current is decreased by a decade, right, or of the order of 10. That is defined as sub-threshold slope. So sub-threshold slope can be defined as dVGS divided by d of log of IDS. In general, it can be explained in millivolt per decade. So that is what we are actually calculating here. We need to calculate what is d log of ID divided by dVGS. This will give me sub-threshold slope, right. So let us do the differentiation here. This will be what? D log of ID, this is ln log is equals to log of constant is 0, or the differentiation of constant is 0, and this will give you what? dVGS divided by n into phi t. So converting the ln ID into log ID will give you a factor of 2.3 log of ID, right. So the sub-threshold slope will come up as dVGS divided by d of log of ID, where this is log base 10 is equals to 2.3 into n into phi t, where n is a slope factor. We have already explained many a times that n is equals to 1 plus gamma divided by 2 times of psi s a. Or you remember, if we derive in terms of capacitances, we said that n is equals to n plus Cb dash divided by Cox dash, right. The minimum possible limit of n is what? 1, which is ideally not possible, right. But the minimum possible limit, if we consider it n equals to 1 also, what is the minimum possible subthreshold slope for a MOSFET is coming out to be 2.3 into phi t. And again the phi t is what? 26 millivolt. So if you multiply 26 with 2.3, you will get around 59.8 millivolt per decade. In general, we can say the Boltzmann limit, or the maximum limit, or the minimum limit of subthreshold slope for the MOSFET is 60 millivolt per decade for a conventional MOSFET. So let me summarize this lecture as in weak inversion, which is also called a subthreshold region, no part of the channel is strongly inverted. The current is basically dominant by the diffusion phenomena and not the drift. A weakly inverted point satisfies the specific surface potential relation, which is linked with the thermal voltage, that is phi t, and the exponential carrier behavior. We have seen that it is related to exponential to the power Vgs minus Vt divided by n times of phi t, right, and that defines the subthreshold slope. We have also seen the body reference and source reference model, which will give you a different perspective. If you really want to find a relation between IDS with VSB, you should opt for body reference, and if you are interested in what is the relation between IDS and VGS, you should opt for source reference model. So we will stop here for today. Until then, take care.